Hi everybody. In this video, we will talk about what a limiting reactant or a limiting reagent is. A limiting reactant is the thing that runs out first, or the thing that can produce the least product. Now that may seem confusing at first, but let's take an analogy. Let's say I wanted to make a cake. In order to make a cake, let's say we need 1 cup of sugar and 1.5 cups of flour, and that will produce 1 cake. So in a way, the reaction for this process is as follows. So what if I said I had 6 cups of sugar, so 6 cups of sugar and 6 cups of flour? How many cakes could I make from that? Well, let's find the limiting reactant or reagent, which is the thing that can produce the least product. So, with 6 flour, how many cakes can I make? Well, I can use a conversion factor because in the reaction, 1.5 cups of flour creates 1 cake. So I could technically do a conversion factor, so 6.5 cups of flour times 1.5 on the bottom, and I guess 1C on the top, and this will get me, I think, 4. So I can make 4 cakes from 6 cups of flour. Now, what about 6 cups of sugar? Well, if it's a 1-to-1 conversion, then for every 6 cups of sugar, I could theoretically make 6 cakes. So I could produce 6 cakes here, and I could produce 4 cakes from the flour. So our limiting reactant in this case is the flour, because with the flour, I can produce less cake than I can with the cups of sugar. And let me prove this. So if we make 4 cakes, then we take, of course, 6 cups of flour. But how many cups of sugar do we use up? Well, if we use 4 cakes, and it's a 1-to-1 conversion factor, then we will have used 4 cups of sugar. So as a result, if we want to make 4 cakes, we have to use 4 cups of sugar and 6 cups of flour. So we used up all our flour, and we only used 4 cups of sugar. And since we had 6 originally, and we used up 4, then doesn't that mean that we have 2 cups of sugar left over? And that's how a limiting reactant works. The limiting reactant in this case is the cups of flour, because this is the stuff that runs out first, and it's the stuff that limits the amount of product we can produce. So in this case, the 6 cups of flour limited us to making only 4 cakes. So if we had more flour, then we could probably make 6 cakes, but since we had only 6 cups of flour, then we could only make 4 cakes, and that just limited everything else, and as a result, you had some cups of sugar left over. So let's try another example. So I'm going to rewrite this, so I think it's 1 cup of sugar plus 1.5 cups of flour makes 1 cake. So what if I had 2 cups of sugar and 4 cups of flour? What would be our limiting reactant then? Well, it's a little bit more complicated, but we can do this. So we can look at each ingredient alone and see how much product each ingredient can produce. So 2 cups of sugar, we know that 1 cup of sugar can make 1 cake, so logically 2 cups of sugar can make 2 cakes. Now what about 4 cups of flour? Well, we can use the conversion factor. For every 1.5 cups of flour, I can make 1 cake. So I would do 4 cups of flour times 1.5, which is the same thing as 1.5, over, I think, 1 cake. And wait, let me write the cups of flour there. And now let's just multiply 4 by 1 over 1.5. So we can actually convert this to 4 times 2 over 3, because I just multiplied the top and bottom by 2, which keeps the fraction the same value. And 4 times 2/3 is just 8/3 cakes. So with 2 cups of sugar, I can make 2 cakes. With 4 cups of flour, I can make 8/3 of a cake. So what's our limiting reactant? What's the thing that's keeping us from making more cake? Well, it's the sugar, because the sugar is allowing us to only make 2 cakes, while the flour can make up to 8/3 of a cake, which is about 2.66 cakes. So obviously, our cups of sugar is our limiting reactant because it can produce less product, which limits everything else. So let's find out how many cups of flour are left after, I guess, 2 cups of sugar are used up. So we know that 2 cups of sugar make up 2 cakes. So our question is, how many cups of flour do we need? Well, we can see that for every 1 cup of sugar we use 1.5 cups of flour. So we can do the math. So 2 cups of sugar times the conversion factor. For every 1 cup of sugar, I use 1.5 cups of flour. And this will give us 3 cups of flour. So we will use 3 cups of flour and 2 cups of sugar in this process. And what will be our leftover? Well, if we have 4 cups of flour and we used only 3, then our leftover is just 1 cup of flour. So that's how you do these limiting reactant or reagent problems, by thinking about which thing produces the least product, and that thing that produces the least product will be the thing that runs out first, and the other thing that won't run out will be the excess. So now let's extend this analogy into the world of chemistry. So in chemistry, just like baking, we can do some reactions. So we can have methane gas and oxygen gas reacting to produce carbon dioxide and water. So when we do limiting reactant problems, we have to balance the reaction, because this reaction is unrealistic since it doesn't follow the law of conservation of mass. And just like how this equation was balanced, because obviously you're not going to use 1 cup of sugar and 1 cup of flour to make a cake, right? You got to balance it out. So in reality, we had to actually use 1 cup of sugar and 1.5 cups of flour to make a cake. So in the same sense, we can't use one molecule of methane and 1 molecule of oxygen gas to produce these two. It's just not physically possible. So let's balance our reaction. So I think I want to balance out the hydrogens first. So if we have 2 hydrogens here, we'll get 4 hydrogens. And let's write out our elements. So CHO, we have, 1 C, 4 H, and 2 O's. And on the right-hand side, we have 1 C, I think 4 O's and 4 H's. And then if we want to make the O's balance out, we just have to put a 2 here. And that will become 4, and our reaction is essentially balanced. So now, since we have a balanced reaction now, we can do a lot more things. So let's now do a limiting reactant problem based on chemistry. So let's just say we had 2 molecules. Note that molecules is not the same thing as moles. Molecules are talking about individual, pieces, while a mole is just, a bunch of them, like 6.022 times 10 to the 23rd of them. So 2 molecules of CH4 and 2 molecules of, oxygen gas. So if this was true, which one would be our limiting reactant? So we can do this by figuring out, how much product does each of them produce? And you see, we have 2 products. So in truth, we can focus on just one of them. So let's focus on CO2. For every molecule of CH4, we produce 1 molecule of carbon dioxide. So it's a 1-to-1 ratio. So if you have 2 molecules of CH4, it can produce a maximum of 2 molecules of carbon dioxide. Now what about O2? Well, for every 2 molecules of O2, we can produce 1 molecule of CO2. So we don't have to do, the conversion factor like we did here, because I can just eyeball it and say, oh, 2 molecules of oxygen produce 1 molecule of carbon dioxide. So I could say for every 2 molecules of oxygen, we produce 1 molecule of CO2. So you can clearly see now which one is our limiting reactant. It is the oxygen gas, since the oxygen gas is the one that's producing the least amount of product, and thus limiting everything else. So in this reaction, we can produce a maximum of 1 molecule of CO2. And just because methane can produce 2 molecules of CO2, that doesn't mean that there's enough oxygen to do that. So there's only enough oxygen to produce 1 molecule of CO2, so the entire reaction will only produce 1 molecule of CO2. So now that we know this is our limiting reactant, let's try to figure out how much CH4 is left after the reaction. So if 1 molecule of CO2 is produced, how much CH4 was used up? Well, we know that 1 molecule of CH4 is used up per 1 molecule of CO2, so it's a 1-to-1 ratio. So if 1 molecule of CO2 was created, then 1 molecule of CH4 was consumed, because it's a 1-to-1 ratio. So we can say that 1 molecule of CH4 was consumed. So if 1 molecule of CH4 was consumed, and we have 2 molecules of CH4, then how much CH4 is left? Well, 2 minus 1 is 1. So we have 1 molecule of CH4 left over. And how much was consumed? Well, 1 molecule of CH4 and 2 molecules of O2 were consumed to produce 1 molecule of CO2. So in all cases, the thing that produces the least product will always be your limiting reactant. So that's an easy way to identify that. So let's write the reaction again on the next page. CH4 plus 2O2 transforms into CO2 plus 2H2O. Let's do it in terms of something different. How about let's do it in terms of dozens? So let's just say I had 2 dozen molecules of CH4 and 2 dozen, I'm going to abbreviate it, molecules of O2. How much CO2 would be produced, and what would be your limiting reactant? Well, let's figure that out. Let's not turn 2 dozen into 24, even though that may seem appealing. But just like a dozen is like a molecule, we can think of a dozen as just, a unit that can be kept consistent, and I'll show you how that is done. So 2 dozen molecules of CH4 can produce 2 dozen molecules of CO2 because it's a 1-to-1 ratio. Now 2 dozen molecules of O2 can produce 1 dozen molecules of CO2 because for every 2 molecules of O2, 1 molecule of CO2 is produced. So it's a 2-to-1 ratio. We can even do the math. So let me do it on the next page. 2 dozen molecules of, I think, O2 times the conversion factor of 2O2 for every 1 CO2. And you get, 2 and 2 cancel out, so 1 dozen of O2. So notice how we don't have to simplify the dozen to, 12. Instead, we could keep a dozen as a dozen, because in chemistry, that's just possible. So now that I erased all of that, we know that our limiting reactant is our oxygen gas once again, and we can produce a maximum of 1 dozen molecules of CO2, because that's a C, sorry. And we would have to consume, I think, 1 dozen molecules of CH4, because for every 1 dozen molecules of CO2 produced, 1 dozen molecules of CH4 are consumed. So this is the stuff that we consumed. So how much CH4 is left? Well, we started off with 2 dozen and we used up 1 dozen. Then don't we have just, 1 dozen molecules of CH4 left? And yeah, that's how you do it. Now, let's scale this up to even grander proportions. So let me rewrite the reaction. CH4 plus 2O2 creates H2O. I think that's a 2H2O plus CO2. So I'm going to mix it up a bit, and I'm going to calculate how much H2O is produced instead of CO2 and see if it gives me the same result. So this time, instead of using, dozens or molecules, I'm going to use moles. So 2 moles of CH4 and 2 moles of O2. What would be our limiting reactant? Well, let's see how much H2O each of them produces, since I'm using a different product, but the answer should still be the same. So for every 1 molecule or mole or whatever of methane, we produce 2 molecules or whatever of water. It's in a 1-to-2 ratio. So if we have 2 moles of CH4, then we have twice as much moles of water, or 4 moles of water. Now, how much water is produced from 2 moles of oxygen gas? So 2 moles of oxygen gas for every 2 moles of water. I think this is a 2-to-2 ratio, or simplified a 1-to-1 ratio. So 2 moles of oxygen would give 2 moles of water. And once again, we found our limiting reactant. That is the oxygen gas, since the oxygen gas produces less product because it produced 2 moles of water here, and meanwhile, the methane produced 4 moles of water. So this will limit our reaction and make us only produce 2 moles of water in total. Now, if we produce 2 moles of water in total, how much CH4 is consumed? Well, we know that for every 2 H2Os, 1 CH4 is consumed. So for every 2 moles of H2O, 1 mole of CH4 is consumed. So we can write 1 mole of CH4 as a part of the stuff that gets consumed. So overall, 2 moles of O2 and 1 mole of CH4 is consumed. So how much CH4 is left? Well, we have 2 moles of CH4 in the beginning, and we used 1, so we have 1 mole of CH4 left. And boom, that's our answer. So if you notice, for all 3 of these problems, I used the same exact numbers, 2, 2, 2, 2, and 2, 2. And yet I still got the same result. I still got the fact that, oxygen was our limiting reactant. And this is because you can read, chemical reactions in terms of molecules, in terms of dozens of molecules, or even in terms of moles, which is the same thing as a molecule, but scaled up to large proportions. So if you notice, for all 3 of these, they're just scaled up versions of each other. At first we start with 2 molecules, which might look like 2 circles, and then we scaled it up to 2 dozen molecules. So 2 dozen would be like 24 of these circles, and then we scaled it up even higher to 2 moles of the stuff, and 2 moles is 2 times 6.022 times 10 to the 23rd molecules. So think of the circle as a molecule, and you kind of realize, these are just scaled up versions of each other, and yet they all still work the same way. So in a reaction, you can read them in terms of dozens, in terms of molecules, or even in terms of moles. And regardless of how you read it, the way that you calculate the limiting reactant is still the same. So that's just an interesting thing that we discovered. So now let's do something slightly different. So let's rewrite the reaction. CH4 plus 2O2 becomes CO2 plus 2H2O. So what if I didn't give you moles or dozens of molecules or molecules? What if instead I gave you grams? So what if I said 20.00 grams of methane react with 23.12 grams of oxygen gas? Can we do 20 grams of CH4 produces, 20.00 grams of carbon dioxide, since it's a 1-to-1 ratio? Well, no, you can't do that, because this reaction is showing you the ratio of molecules, not the ratio of masses. So in the previous three problems, they were all referring to molecules in some way or another. 2 molecules is a molecule, 2 dozen molecules is still talking about molecules, and 2 moles is still talking about molecules. It's just, a lot of them. But in this case, grams is not molecules. So how do we convert grams to moles? Well, molar mass. So I'm not going to show you how to do that because I did that in previous videos, but we know that the molar mass of methane is 12.01 plus 4 times 1.01, and using my calculator, we get 16.05 as the molar mass of methane. So we simply take 20 and divide it by 16.05, and we get an answer of 1.246 moles of methane. Now let's do that for oxygen gas. Now oxygen gas contains 2 atoms of oxygen, so each atom of oxygen weighs 16.00 grams per mole. If you have 2 of them, then doesn't that just mean it's times 2? So the molar mass of O2 gas is 32.00 grams per mole. And if that's the case, then we can convert the grams of oxygen gas into moles of oxygen gas. So 23.12 divided by 32 will give me a grand total of, 0.7225 moles of oxygen gas. So now what do we do from here? How do we find the limiting reactant? Well, remember how we have to find the reactant that produces the least amount of product. So let's get going and do that. 0.7225 moles of oxygen gas can produce how much carbon dioxide? Well, for every 2 molecules or moles of oxygen gas, we produce 1 mole of carbon dioxide. So it's a 2-to-1 ratio. So let's, multiply this by the 2-to-1 ratio, 0.7225 moles of O2 times the 2-to-1 ratio. So we have 2 O2 on the bottom and 1 CO2 on the top. And notice how we're just dividing by 2. So thus, we will just divide 0.7225 by 2. And we get that we produce 0.3613 moles of carbon dioxide. So let's see how many moles of, carbon dioxide can be produced from methane. So it's a 1-to-1 ratio for methane carbon dioxide. So if we consume 1.246 moles of methane, then we will produce 1.246 moles of carbon dioxide. So notice how the oxygen gas produces less product than the methane. So therefore, oxygen gas is our limiting reagent or reactant. So let's find out, if we produce this much carbon dioxide, how much methane is consumed. So if we know that it's a 1-to-1 ratio, then if we produce 0.3613 moles of carbon dioxide, then we, of course, consume 0.3613 moles of methane. So this is the full reaction, 0.7225 moles of O2 and 0.3613 moles of CH4 combined to form 0.3613 moles of CO2. So, knowing this, how many moles of CH4 are left after the reaction? Well, originally we had this, and after we consumed this much, so how much is left? Well, if we had this much and we consume this much, then we just subtract them to see how much there's left. So, 1.246 minus 0.3613, and I get that we have 0.885 moles of methane left over, and that is the answer. And if you wanted to find how many grams of methane were left over, you would simply convert this number into grams using the molar mass. But I'm not going to do that right now because we have one more topic to cover. So the next topic we are going to cover is percent yield. Percent yield is equal to the actual yield, so actual yield over theoretical, so that's an H and that's an E, and yield, and times 100%. So what is yield? Well, yield is just the stuff that you get. So, for example, the theoretical yield is the yield we've been calculating, assuming 100% completion. So in this problem, for example, we assumed that all the oxygen was consumed to produce, the water. So in theoretical yield, you assume that it is going to be 100% complete. But in actuality, reactions don't actually go to 100% completion. So this is less than 100% completion. Although some reactions can go very close to 100%, nothing is really perfectly 100%. And that may be due to measuring errors, or maybe just the reaction not wanting to go all the way forward. So the actual yield is what we observe in real life. And the theoretical yield is the thing that we calculate, just like how we calculated it over here. So let's do a practice problem. Let's just say that we had this reaction going on, and real scientists actually, did this experiment, and, they calculated the theoretical yield, and they were like, oh, okay, our theoretical yield was this, assuming that all of the oxygen was consumed as a limiting reactant. So, assuming that's true, then scientists assume that, 0.3613 moles of CO2 were created. So the theoretical yield was, 0.3613 moles of carbon dioxide. And remember, this is assuming that this reaction was 100% complete and that all of the limiting reactant, in our case, oxygen, was consumed. Now, in reality, let's just say that they measured the CO2 and they measured that, we only had 0.3214 moles of carbon dioxide, so they wanted to know what was our percent yield. So percent yield is actual yield, which is what is actually measured, over theoretical yield, which is what is assumed to be true, using, calculations, and multiply by 100%. So if we type this into a calculator, 0.3214 divided by 0.3613 times 100%, we get a number such as 88.96%. Oh, I went to the next slide. Sorry for that. And that is our answer. So this number means that the scientists got 88.96% of the product that they expected that they would get. So the expected stuff was the theoretical yield, and the actual stuff was, the actual stuff that they got. So they got 88.96% of the carbon dioxide that they expected to get from the reaction. And note that when you're comparing the actual yield and the theoretical yield, they have to be in the same units. So if you're comparing moles of CO2, they both better be in moles of CO2. If you're comparing them in terms of grams, then both of them better be in grams of CO2. So either way, they both have to have the same units on the top and the bottom. Because think about it, they have to cancel out, so they have to be the same. And that's all for this video, and have a nice day!